Hello, welcome to another Year 10 Chemistry revision video. Today we'll be looking at the 2017 Double Award Higher Tier paper. Okay, question 1. The Earth's atmosphere has evolved over millions of years to its present composition, and the pie chart below shows the composition of the atmosphere at one stage of its evolution. Describe the main differences, we're looking for big differences here, in the composition of the atmosphere shown in the pie chart and that present on Earth today. The first thing I spot is that carbon dioxide percentage is much too high. Carbon dioxide now is 0.04, so it's decreased from 18%. And the other one is there is no oxygen in this pie chart whatsoever. So the current atmosphere contains oxygen, and I made a little mistake there. It doesn't contain 18%, it contains 21%. So there we go. Complete the table to describe the simple chemical test that can be used in the lab to identify hydrogen and carbon dioxide. The first one for hydrogen, we're going to put a lit splint into the gas and we're going to expect to hear a squeaky pop. And for carbon dioxide, we're going to bubble the gas through lime water and we're going to expect to see the lime water turn from clear to cloudy. During the last 250 years, the level of carbon dioxide in the atmosphere has increased. Most scientists believe that the increase in the level of carbon dioxide in the atmosphere has resulted in global warming, and the table below shows some data about the atmosphere between 1750 and 2000. First thing they want us to do, describe that trend in average global temperature between 1750 and 2000. So my average global temperature column is the one on the right, and 750 to 2000 is the whole of the table. And look, I've got to get 2 marks here. So first mark is going to come from saying that the global temperature has increased over time. The second mark, what I want you to spot, is for the first 150 years, it only goes up by 0.4 degrees, and then it goes up by 0.9 in 100. So the second part is for saying the rate of increase has also increased. For the next part, they want us to calculate the percentage increase in the concentration of carbon dioxide in the atmosphere from 1750 to 1850. Well, I'm going to be looking at this column here now, concentration of carbon dioxide, and I've circled the 2 concentrations. For 1750 is 278 and 1850 is 288. If I want to work out a percentage change, I do change divided by original times 100. So I'm going to do the change, which is 10, divided by the original, which was 278, times 100, and that gives me 3.6%. Next one now, I've got the following table gives some information about some atoms A to E. Now, what I'd love you to do here is when you see these tables, make sure you have your periodic table to hand, or you know that you've got to be looking at the back. So the first one they're looking for is the element A to E with a mass number of 12. Remember, that word mass number means protons and neutrons added together. So 6 plus 6 gives me 12, so it's E. The next one, we're going to give the letter A to E of the atom found in group 1. Now, there's 2 ways of doing this one. I worked out here is 11 protons is 11 electrons, which would mean I have a configuration of 2, 8, 1, and that 1 means I'm in group 1, so I know it's D. The other way that I could work this out is I could use the proton numbers to work out what element they are, and then use the periodic table to work out, well, which element is in group 1. So for example, if you have a look at your periodic table, A has 12 protons and magnesium has 12 protons. Magnesium is in group 2, so it's not A. B, 10 protons, is neon, that's group 0. C and E, 6 protons, that means we're carbon, which is group 4. And D, 11 protons, is sodium, which is in group 1. Choose the letters A to E of the atoms that are isotopes and give a reason for your choice. Well, hopefully we can remember our definition of isotopes, which we're looking for the same number of protons but different neutrons. And the 2 which match that definition are C and E. They've both got 6 protons, but they've got different neutrons. Look how I've put the number of protons in a bracket as well. The diagram below shows the electronic structure of an element in the periodic table. Now, what I've done first is I've counted up those crosses to get 10 crosses, and then I've worked out that that is neon, because neon has 10 electrons. They then want me to use an X to represent an electron, just like above, to draw the diagram to show the electronic structure of the element which lies below this one on the periodic table. So I found neon, and I went below that and found it was argon. Argon has got 18 electrons, so I should have 2, 8, 8. They then ask why both of those are chemically unreactive. Remember, that is because they have a full outer shell. And they may ask you, why are they inert? That's another word for unreactive. I've then got a lot of information here about the hard water practical. Now, I'm not going to read all of the information to you here, but we're going to be looking at the hard water practical using soap solution, and we're going to be measuring the volume of soap required to produce a given lather. Now, what I've done is I've made some notes here on each type of water for you. We've got 3. Well, sample A requires 8 before boiling and 8 after, so a high amount of soap before and after, which means it's permanent. B requires 12 and then 6. So it is very hard before, and then it has been softened slightly. It's not completely soft, so that means that it's a mixture of temporary and permanent, because the temporary hard water was removed with boiling. And finally, C was very hard before boiling with 15, but was completely softened after boiling to 2, which means it's only temporary hardness. And finally, look down the bottom. They've told us they use distilled water, which is soft water, and they noticed that it only required 2 centimetres cubed, so that is the soft value. Which of these statements best describes the water samples before boiling? All 3 of them before boiling were hard, which means they all contain magnesium or calcium. What is the purpose of testing the distilled water? It acts as a control, and a control in an experiment is something for us to compare against. In carrying out the tests on the samples, which variables need to be kept the same each time? Well, I know each time for all of the results, the volume of soap was different. So statement 1 can't be that one, because it said that's going to be kept the same. I'm not going to keep that one the same. And finally, look, I'm not going to keep that the same. The 2 things that I keep the same are the volume of water and the number of times shaken. Finally, which one of these statements best describes water sample B? Well, we've just spoken about this. B was a mixture of temporary and permanent, and the reason was because the volume of soap required to form a lather decreased after boiling, but is still higher than the distilled soft water. In your opinion, do the advantages of living in a hard water area outweigh the disadvantages, and give 2 reasons to support your answer? Now look, they've asked you for your opinion, so you have got to pick a side. If you decided that yes, it's good to live in a hard water area, you've got to give me 2 reasons. And those 2 reasons are, it strengthens bones and it improves teeth health. You could have also spoken to me about the improved taste. If you said no, what I want you to be getting there is that you either say that it forms scum with soap and it forms limescale when heated, making appliances less efficient. We've then got some information here on the gas syringe practical. And at the top, the magnesium ribbon was reacted with an excess of dilute hydrochloric acid. Remember, that word excess means too much, so the whole reaction will occur. The volume of hydrogen produced during the reaction was measured over time using a gas syringe. The experiment was carried out at a temperature of 20 degrees. The table below shows the results obtained in the experiment. Now, we're going to have to plot the data on the grid opposite and draw a suitable line. You're also going to have to select an appropriate scale for them. Just remember, time, my left-hand column always goes on the x-axis, the bottom, and my right-hand column goes on the y that's pointing to the sky. And then, after plotting that, going to have to add another graph called B. And I'm now going to sketch the graph that would be obtained if a piece of magnesium of half the length were reacted. Now, what I want you to remember, if we react something which is half the length, it's going to produce half the amount. So rather than producing 100, we're going to produce 50 of gas. And I will go over to the next slide now for you so you can see your answers. So for your graph, what we're looking for time along the bottom, you go up in 10s, and for volume of gas, you go up in 20s. We then check each of your points are in the exact spot. This is something that we cannot be rushing, and that you have got a smooth curve. Remember, that curve can't look like it's been sketched. It's got to be nice and smooth and one continuous line. I've then done for B. You get 1 mark if your line is halfway up. So look, I finished at a 50. And then because there are less magnesium particles, it's going to be a slower rate. C. If the original experiment were repeated at a higher temperature, the reaction would occur at a higher rate. Explain this using particle theory. Well, remember, higher temperature means particles move faster, so there is a greater chance of successful collisions. This method can be used to investigate the rate of this reaction. Without changing the method or apparatus used, state what should be done to improve the overall strength of the evidence collected. If you want to improve your confidence in results or improve the strength of the results, you're going to repeat the experiment and then you're going to calculate a mean of the repeatable results. And when we say the repeatable results, that means we're not going to use the anomalies. Give an advantage and a disadvantage of using the following apparatus to collect the hydrogen gas. Well, first thing I can see what's going to happen is the gas is going to bubble through the delivery tube up into the measuring cylinder, and the volume of gas is going to be identified here. It's going to push the water level down. First thing that I can spot is the bung is already on, so that means no gas is going to escape. So my advantage of all of the gas produced gets collected, no gas is lost. My disadvantage is as the bubbles move into the measuring cylinder, it's going to make the water surface move, which makes it difficult to read the volume. Now our next question here, we've got the diagram shows some reactions of chlorine. Give the chemical formula for substances A, B and C. If you see the formula, we're looking for top, swap, drop. But we first need to work out what each compound is called. So let's look at orange solid A. In orange solid A, chlorine is reacting with hot iron wool and it forms an orange solid. Well, that means if iron and chlorine react together, I'm going to form iron 3 chloride. To then go ahead and do top, swap, drop, I look at the back and I see that iron 3 is Fe3+, and chloride is Cl-. And when I go through top, swap and drop, which I'll show you here, I end up with Fe1Cl3. I then do the same for B and C. Well, for B and C, I've got chlorine plus sodium bromide. Well, chlorine is more reactive than bromide, so it's going to steal the sodium. So I know that B is going to be called sodium chloride, which leaves poor old bromine on their own. And that's my halogen C. So when I do top, swap and drop for sodium chloride, I get NaCl. And bromine, like all of the halogens, doesn't like being lonely, so it will always come in a pair, will be Br2. State, giving a reason, the main safety precaution that must be taken when carrying out these reactions. We're going to have to do it in a fume cupboard, and that's because the halogen fumes are toxic. State and explain how the observations for the reaction with sodium bromide would be different if the chlorine were replaced with iodine. Well, this time iodine isn't as reactive as bromine, so no reaction will occur, as iodine is less reactive than bromine, so it will not be able to displace it from the solution. Chlorine can form a number of compounds by reacting with oxygen gas. One of these is used in water treatment. A sample of this compound contains 0.71 grams of chlorine and 0.64 grams of oxygen. Calculate its simplest formula. Now remember, that word simplest is often interchanged with empirical. So first thing we're going to do, we're going to draw our empirical formula table. I've got a column for chlorine and a column for oxygen, and I put the mass of each at the top. I've then divided each number by that element's mass number. So chlorine 35.5, oxygen 16. I then circle the small number and divide both columns by that small number, and that gives me chlorine an answer of 1 and oxygen an answer of 2. Well, that means my simplest or empirical formula is Cl1O2. Silver nitrate solution is used to detect the presence of halide ions in solution. The equation below represents the reaction between silver nitrate solution and potassium bromide solution. Write an ionic equation for the reaction including state symbols. State symbols, everybody, are these brackets here. So what they're looking for is the reaction between the silver and the bromine. So look, I've scribbled out the NO3 and the K. So I know I'm going to have Ag plus Br to give me AgBr. Well, I look at the back. When I look at the back, silver is Ag plus, and it's a solution. So it's AQ, aqueous. Plus bromide, which is Br minus, which again is a solution. And that gives me AgBr, and we've got to remember that this is bromines. This would be our cream precipitate, and a precipitate is a solid. 2. Write the balanced symbol equation for the reaction between calcium iodide solution and silver nitrate. Now this is a top swap drop, so I'll give you how we can work this out at the beginning. I know I've got calcium iodide, and it's going to react with silver nitrate. So what happens here, everybody, is the non-metals swap around. So that's going to give me calcium nitrate plus silver iodide. And I look at the back for each of those elements on the ions table, and then I do top swap drop to work out their formulas like I've done here. And finally, we need to put 2's to balance. The balanced symbol equation for the reaction between sodium and oxygen is given below. 4Na plus O2 gives 2Na2O. Calculate the mass of sodium oxide, which is there, that should be produced when 0.3736 grams of sodium is burned in air. So I know the mass of sodium, so that's why I put a K for known, and I don't know the mass of sodium oxide. Now we should be remembering, if I have a known and an unknown, this is what we call a reacting mass equation. Now I've given you the reacting mass equation there. Unknown mass equals known mass over known MR times unknown MR. So first things I'm going to do is I'm going to work out the MRs of each of the two things I'm looking for. So for 4Na, I've got 4 sodium, so 4 times 23 is 92. And for 2Na2O, I've also got 4 sodiums, but now I've got 2 oxygens. So I've got 92 plus 32 gives me 124. I then plug those numbers in, so I've got 0.736 divided by 92 times 124, and that gives me a reacting or predicted mass of 0.992 grams. When the reaction was carried out using 0.736, it was found that the mass of sodium oxide formed was actually 0.338. So rather than making what we predicted, we actually made that. Use your answer to calculate the percentage yield. So what we're looking for is a percentage of what we should have made. Well, we actually made 0.338, so I divide that by what we should have made, 0.992, and it's a percentage, so I times it by 100, and that gives me a percentage yield of 34. Part 2, if no product was lost, suggest one possible explanation for the percentage yield not being 100% is an incomplete reaction. We haven't allowed it time to finish. Last question. Describe how the reactions of lithium, sodium and potassium with water can be used to show the trend in reactivity in group 1. Explain this trend in terms of electronic structures of the elements. So I have got 2 parts. First part is I've got to describe the reactions of lithium, sodium, potassium in water. And then I have to explain what we see in terms of electronic structures. So part number 1, I first state that group 1 elements get more reactive down the group, and this can be shown in their reaction with water. And here we go for the observations. Lithium fizzes and moves slowly on the surface. Sodium fizzes and moves quickly on the surface, and it also forms a ball or sphere and melts. And potassium fizzes, moves quickly and forms a ball, and it also ignites with, and I'm going to change my word there, with a lilac flame. So that's my first part done. Now I'm going to explain in terms of electronic structures the elements. What we've got to remember, they're all in group 1. So all 3 metals react by losing their outer electron. And as you go down the group, the electron gets further from the nucleus, so it's more easily lost. That's the video finished. If you've got any problems, please come and find myself or any of the other teachers in the science department, and we'll do our best to help answer any of your questions.